Supermatrix methods, and let me just start with reminding where we stopped last time. By the way, I understand that 30 copies of the first and second lecture should be available outside, as far as I understand. Somewhere I was promised that they will be placed.
These they will have to take it.
Already, okay. Okay, then at least 30 lucky, or I don't know, maybe unlucky persons. Those. If you feel that you desperately, absolutely need a copy and you do not have one, I can try to produce it just manually afterwards.
Yeah, we can make it
2
or 3 more. So
yes.
Chris Marks can be taken care of. Rainer Kuhn.
Okay. Or alternatively, we can arrange maybe copying, just scanning my transparencies and giving PDF files to people.
Yeah, we discussed that too. That this could be made available online. Yeah. And then you can just look at it there with your laptop or with a computer.
Okay, our main object that we started to investigate. Little n, yes, thank you. So this was our main object of interest. I guess now, after a few other lectures, you realize, in fact, why. Martin already made some comments why we're interested in this stuff, because these inverse determinants, they're intimately related with resolvents, as you probably already guessed. So what I tried to develop are systematical tools of investigating resolvents of random, in general, random operators, but I start with finite dimensional operator random matrices, the simplest possible case of random operators. So if it was not clear up to now, I hope it slightly clarifies our interest in that. But resolvents turned out to be more complicated objects and simpler but still relevant objects, just inverse determinants. So we started to consider them, and we arrived at the last formula that we write that at the formula at the okay, we should center it and try to make it, just be careful. Okay, I think it's okay, it fits. So the last formula which we more or less derived was a kind of integral representation for this object for arbitrary z's, provided imaginary part of every z is non-zero. It could be positive, negative, but it was not allowed to be 0. Although, as I commented, eventually we will be interested in extracting behavior when this imaginary part approaches 0. So it also should be kept in mind. So this general correlation function of inverse spectral determinants, given in terms of integral, okay, there is some constant of secondary importance for us, could be found if we are interested. Integral goes over Hermitian positive semi-definite matrices, R, and 2 other objects which enter this formula. Just let me remind you, because most important objects for us. Matrix S is diagonal matrix made of signs of imaginary part of individual z, and matrix Z is diagonal matrix made of z's. So with this notation, I think everything here is well defined. N, capital N, is size of our random matrix. So H is a random matrix of size n by n with Gaussian probability density that we discussed last time. And small case n is the number of terms in this product. So this formula is valid for arbitrary n, which is larger or equal than small case n. And following our general route, at the next step, we just rescale r with replace integration variable r to nr. This produces r as r squared. It produces n squared factor divided by n in front of this term. And obviously, it also produces n in front of the first term. And using the fact that determinant, just rewriting determinant raised to power n as exponential of n log that, which is the same as trace log of r, we will get also term of which has n in front, one more term which has n in front in the exponential. So it's just all reminiscent of what we had for the simplest case n equal 1, and we will try to exploit to extract large n behavior just by using saddle point analysis. In order to simplify and for illustrative purposes, I consider the simplest. I always will try. I think also Leonid did this. Try to consider the simplest, in my mind, non-trivial case for didactic reasons. And in this setting, the simplest case is obtained if you just set all real parts of these z's to 0 and consider all modulus of imaginary parts. They can be of different sign, but you consider them just of the same magnitude. And we call this epsilon. I tried to systematically mark epsilon in red just to stress the fact that it will play an important role in our analysis. But eventually we will be interested in epsilon tending to 0, and we shall see how fast it should tend to 0 in order to produce something non-trivial. In fact, we will see that it should scale with n appropriately. Okay, after these simplifications, we just see then z, under this assumption, z is just I times epsilon times S matrix itself. And our integral is written, it takes this form. Now, let us start analyzing this from the simplest possible case. When S is just identity matrix, it means that all signs of the imaginary parts are either all positive or all negative. This is a somewhat trivial case, trivial in the sense that the result will be more or less trivial generalization of n equal 1 case. But we should start just to set the background for further discussion. So if S is just plus or minus identity matrix, then we see, okay, we see that it just, okay, because of this fact, it just trivially drops out of this expression. And now we proceed as follows. We just diagonalize R by unitary rotations. We already seen this decomposition earlier when we derived, in fact, that formula, but let us use it again. We know how the measure dr looks in these new integration variables. It contains, we discussed it last time, it contains so-called Vandermonde factor to power 2, a product of all differentials of these diagonal entries R, which are positive, please remember, non-negative, better to say. And V, what is most simple, this situation is simple because V just goes away, because a trace of R squared, we obviously by cyclic, you just immediately see that by cyclic permutation that it's just by unitarity it vanishes. Here it's obviously vanishes by the same reason. modulus of determinant of v is 1, therefore it also vanishes, disappears here. So integrand does not depend on this v, and what remains is purely integral over small case n individual diagonal entries of this matrix eigenvalues. And this integral can be performed by the same saddle point analysis that I presented for n equal 1. There is slight complication, but this is of secondary importance for us. Complication is that the terms in front of our, we have the structure of the integrand is as follows: exponential minus big parameter n, which justifies our presumably our saddle point evaluation, and some factors in front which do not contain this parameter n, and therefore they are irrelevant for finding saddle point of dominating this integral. But this factor vanishes, in fact, as we shall see. Just investigating relevant saddle points, you find that those compatible with positivity of r is the only possible choice. Just all r's equal to each other equal to 1. And we immediately see that if we just, what is a general recipe for calculating integrals by saddle point method? You should find these saddle points and then do two things in general. You should expand up to quadratic form in the exponential and perform Gaussian integration. This will give you a factor, so-called fluctuation factor. And you should just replace, substitute these values, saddle point values of r, to terms which do not contain this large factor. But here it's small complication that prefactor just vanishes at this point. It's not a problem at all. You should just expand to higher terms and take care of this. It's easy to develop saddle point method. It's not real difficulty. It's technically it's unpleasant because you should expand to higher order terms. In fact, in this setting, it's even for this particular integral, one can so-called Zelberg integral takes care of all calculation. But even in general setting, if your pre-exponential term vanish, you should take care of it by expanding it further and finding first non-vanishing term.
So you have to go beyond the Gaussian approximation.
Yeah, essentially, yes, but it's not a big deal. It could be technical difficulty, but it's not real problem.
But the 0 is order n, right?
Small case n. Small case n. Nothing contains capital N which controls your saddle point approximation apart from it's an exponential. Because you see, number of these alphas, 1, 2, up to small case n, number of terms in the product. And this is, in our analysis, we consider this to be of order of unity. It can be 100, but it's fixed. And n, capital N, goes to infinity.
But I'm confused because the van der Waals came from doing this orthogonal change of variables. Right?
Precisely. Matrix, let us discuss. This matrix R was the matrix of the size small case n times small case n, and this is precisely the number of terms here. So if you deal with just 1, it will be 1. If it's 2, 3, 100, but never n, capital N, which is eventually sent to infinity, this capital N sent to infinity. So it's slightly more complicated than standard saddle point analysis, but it's not conceptual difficulty.
Actually, I don't quite see why you need to go to the eigenvalues. Why can't you just do the saddle point analysis on the upper formula?
Because then,
The matrix.
You can do it in this way, but there are some, this is, I would say, it's more clear because you have, in fact, product of one-dimensional integrals, and you can do, if you really like to seriously do analysis of various saddle points, it's easier in this language than on matrix language. But in principle, you can do it on in a matrix
But
way.
if you did it in matrix, would the same problems appear with the...
Yes, if they will be hidden, because your pre-exponential still...
No, the problems do not appear.
That's the
They
question.
just do not appear.
Because you claim that this factor appears only if you go to this representation, right?
Oh, I think you're making the problem harder. I mean, you're reducing it to a product of one, well, apart from the van der Waals, you have a product of one-dimensional integrals. I can see that this maybe is something that you like, but the price you pay is if you have this
Yes.
more complicated saddle analysis.
Okay.
And, these problems do not appear if you do it in the upper.
Okay, but I would anyway.
This is not your point.
Yes.
You're getting to
Yes.
something else.
Yes.
It's not-
This is that if this is a technical problem, it's of secondary importance. It's clearly solvable, and one can do it in one way or other. It's not conceptual problem, which we will discuss. Yes. Probably we should not even call it a problem, just some small technical obstacle. Okay. However, the main point really, which should be that this simple evaluation go through without modulus this what we discussed without any problem if only if all imaginary parts are of the same sign. Otherwise, if at least one of them is of different sign, then S is already non-trivial matrix, and what happens? You still can try to diagonalize. I always thought this is the way of analysis. So on.
Excuse me, you wanted to use both of them?
Yes. Thank you. Just always forget about this luxury of having two. Maybe I restore the previous one. Just not that I need it much, but okay, let it be here. Should we focus it more? Or not? Okay, I think it's visible, right? So what happens? This trick doesn't work because you see that with S present, your integral, this term trace of RS squared depends, in fact, of 4 of these V's. In general, I'm not aware of any method of performing integrals with 4 V's. With 2 V's, there is hope, because there are famous Harishchandra-Isaacson-Zuber formulas, but okay, this does not help. However, just thinking about this problem, one can find, in a sense, a way out. Namely, suppose that we make a transformation just R conjugated with T and Hermitian conjugate of T, where T is some non-singular matrix. Then we immediately see that this transformation imposes the following change of trace of RS squared, I mean, obvious. Now, if we require that T are not just arbitrarily non-singular, but they satisfy the following identity, that T Hermitian conjugated times matrix S that we have, which is not identity matrix in general, but matrix made of plus and minus 1, at least 1 plus and 1 minus present. So if T satisfy this identity, then we see that trace of RS squared just goes to itself. So it's invariance, it's practically our exponent, then expression in the exponent will be invariant with respect to such a transformation. Moreover, because modulus of S, diagonal values of S just plus or minus, modulus is 1, they are plus or minus 1, modulus of determinant T is 1, and there we see that also term determinant of R in pre-exponential factor just is invariant. And what is also very important, that if we multiply matrix R, Hermitian positive definite matrix, with non-singular matrices, there is a simple theorem, I think it's known in the textbooks on metric theory as Sylvester law of inertia, that the number of positive and negative eigenvalues, in fact, does not change if you multiply with non-singular matrices. And therefore, the domain of positive definite Hermitian matrices goes to itself under this operation. There is only small, everything is completely fine with this invariance apart from this term which involves epsilon, because epsilon tries R goes to something non-trivial involving t. However, epsilon is small in some sense, because I mentioned that we will be interested in finally in epsilon going to 0 in some way. So we can probably expect that, okay, this is not that high price for observing this invariance. So for concreteness, let me assume without reducing any generality that just first p entries of matrix S, they are +1, and the remaining q entries are -1, p plus q equal to the size of matrix N. The matrices T which verify this identity, they in fact form the so-called pseudo-unitary group UP, Q, and they will play the most fundamental role in all development from now on. How we use it for our purposes? Okay, I leave it here. Go here. Okay. So this invariance, which is also known as hyperbolic symmetry, you will see why it's called hyperbolic later on.
Also due to Franz Wegner, whom we heard about earlier.
Yes, and Wegner's name will appear many times, even though I usually do not mention authors of various trees. I think Wegner will appear intermittently on these notes. So, according to Martin, this name was coined by Franz Wegner, hyperbolic symmetry, with good reason. We will see that it related to some hyperboloids anyway, if you do not see it immediately. And this can be exploited to perform our task of evaluating Lagrange limit of this integral. Before doing that, or for doing that, it's convenient just to introduce r times s as a new integration variable in our integral. So instead of integrating over Hermitian positive or non-positive semi-definite matrices R, to consider R as integration variables R times S, we see that everything in the exponent depends essentially on R times S, so it's a very natural thing to do. And determinant of R can be very easily converted to determinant of R times S because of product of determinants, so it amounts to trivial factor in front. So we can if we think it's helpful, write it in this way. Now, I leave for you as an exercise. Again, when I mean as an exercise, for arbitrary, you can do it for arbitrary n, but just always try, if you are interested in understanding things, try to do it for the simplest case, non-trivial case, n equal 2. And you will learn everything, practically everything on that example. So just verify that such non-Hermitian, that's important thing, non-Hermitian matrices are S. Nevertheless, provided R was positive, it's very important point. Here R must be non-negative. In this case, even positive in this point. If they are positive, then RS are diagonalizable by precisely these pseudo-unitary similarity transformations from that group U, PQ. Again, there is some, as Martin called it, redundancy in this. So we do not need all, in order to make this correspondence one-to-one, we again should factorize these simple diagonal factors which drop out. So really, one can use the full group, but then it will be a degree of redundancy. One can, but anyway, what's important that these matrices are first diagonalizable by precisely these pseudo-unitary rotations, and all eigenvalues, these R to R1 to Rn of this Rs, they will be real, and precisely Q of them positive, the rest being negative. So this is very nice property. In order to make our discussion most explicit, we consider the simplest non-trivial case, p equal q equal 1, which amounts to n equal 2. P plus q is n, so n equal 2, p equal q equal 1. So S is basically Pauli matrix 1 minus 1. Sometimes in the literature you find this notation sigma 3. Then RS is parameterized in this setting. I write it in this way. I write minus here just to use. I think it's convenient to deal with positive numbers, so I put minus here. But according to our discussion, one of eigenvalues must be positive. The remaining is negative. T here is from this factor space. In fact, it's clear that we do not need, as I mentioned, these factors, because they do not play any role. If you multiply T with them, they will just, because of diagonal structure of this central matrix, they just drop out. So we should factorize by them. And also, obviously, we can restrict to determinant T equal 1 by obvious reason of presence of T minus 1. So it's from SU 1, 1. Okay, now you can also calculate measure.
So maybe we just summarize here.
Yes.
Because Jan absorbs this factor S that multiplies from the right into R, he now has a non-Hermitian matrix. And he wants to diagonalize it again. And in general, we know that non-Hermitian matrices will give you complex eigenvalues if they are diagonalizable at all. So you may actually lose the property. But here, the eigenvalues remain real, and they do so for a reason that's not explained usually in basic linear algebra. However, it doesn't go far beyond it. Sort of
in Gantmacher book there is
what
some
you learn in
explanation.
relativity theory. The space now has this diagonal matrix S plays the role of the sort of Minkowski metric, where here now we have P time-like directions and Q space-like directions, and you should diagonalize by a Lorentz transformation, which is the analog of this non-compact group UP comma Q, and then it's important that the diagonalizability by real eigenvalues really is exactly true because R is positive. If you went just a little bit further, you would lose it. So there's actually there's a bijection between two spaces that makes this very clear. So you use exactly the property R bigger than 0 that to ensure that this thing can be diagonalized with real eigenvalues.
Thank you, Martin. Oh, yes, please.
How is it that you only factor out U1? Because there would be other diagonal matrices also in this hyperbolic group which you could factor out as well, right?
You mean?
The second one that is taken forth by the S.
Yes.
Pardon?
You could write U1 comma 1
Yes.
and factor out 2 U1.
With two U1s. Yes, yes.
What
You want on? Yes, yes, yes.
But you're writing SU1 comma 1. That
Yeah.
already takes away 1 U1.
Yes, yeah. Just determinant, a fixed determinant.
I see. I understand.
Okay. Yes, please.
So is it important to know all the T matrices that you could use, not just one?
No, you see, every maybe I misunderstood your question. Every given, if you have given R multiplied with S, it will be diagonalized by its own matrix T. But as we integrate on them, effectively this means that we will integrate all these T's, and you will see this integration plays a crucial role. This will be in the heart of the whole development. Okay, just again as an exercise for 2 by 2 matrices, you can calculate in these RT variables the measure. If you are not happy with invariant measure on this T, and you will see it either in the next view graph or maybe one later. So you will see explicitly these things. But for the time being, it will be something depending on R, will be Jacobian factor, and will be some measure on T, which I claim to be invariant measure. And we are interested just in general in understanding general structure of our integrand after this just using all these facts. We see that basically, okay, we have just external, I would say, or integrals over R1 and R2, and because of this diagonalizability, we see that T's just vanished from the exponential altogether, apart from a term containing epsilon, and this is basically, this amounts to that invariance which I already discussed in general terms. And so I write it in such a way that it's suggestive of performing large N analysis again with respect to R1 and R2 by saddle point method. But there is non-trivial factor, which is in itself an integral over all these T's. So this explains. So we need still to integrate over all these T's. If it hadn't been for this epsilon, it would be integrand would be completely independent, but this would be disaster because these T's are parameterized by hyperbolic functions. They live not on, say, a sphere, but on a hyperboloid, so it will be divergent integral. So it's in fact epsilon keeps it living infinite, and it's not a nuisance, but it's an important part of the theory itself. However, if we like to perform this integral by evaluate the asymptotics of this integral when n is large, we see that we rather should keep epsilon times n in this limit n to infinity finite. And I will use notation epsilon times n equal to variable eta. And I assume that when n tends to infinity, simultaneously epsilon tends to 0, and this product is kept fixed. And I will analyze my integral under this condition. So you see that really epsilon becomes, when n, in this way, we see that what we are doing, we're in fact increasing the size of our matrix and shrinking distance to real axis, because epsilon was distance from the real axis of all these z's. So we in fact come closer and closer to real axis where all eigenvalues of our Hermitian matrices lie, to poles of these inverse determinants, and in this way we probe their properties. This is how it happens. So it's a very meaningful procedure.
Is there any restriction on the size of eta?
No. Eta from 0 to infinity. Okay. Now, we just do, by the way, what's nice here, that here there is no this problem. We see that here we have something like a Vandermonde square, but because of one of these r's change its sign, they sum up, not they subtract. So there is not this problem of vanishing integrand, which is pleasant. We are happy, even Martin probably happy to do this evaluation now, and we end up with basically we see that in this limit, which I explained in detail, our correlation function now of two inverse determinants, one which has spectral parameter above real axis, second which has below real axis, is practically determined by the value of the distance to the real axis, this parameter eta, it is scale distance. And still we need to perform this integral. Our matrices Q are just, after we performed this saddle point evaluation, diagonal values R1 and R2 are now ones. Remember that R2 came here with minus sign, so if this is 1, this is 1, this is S, matrix S. So we see that basically the integral is reduced in this limit to integral over manifold of matrices parameterized as T, S, inverse of T. And such matrices, they obviously satisfy, for example, the following important constraints. Q squared equal 1, just multiply Q and you see T just drops out. Trace Q equals 0. And this is the first example in our lecture that we encountered an object, a particular case, the simplest variant, the so-called zero-dimensional variant, of the object which physicists call nonlinear sigma model. It's just fancy name. It has history behind it, so it's not just was invented from nothing. I won't go into it, but important thing that basically it's integration of manifold of saddle points, because basically we had just, if we consider, as Martin suggested, taking saddle points just in matrices, we will see that basically we should take into account integrate not over isolated saddle points, but of the whole manifold of saddle points controlled by this parameter eta, this integration controlled by this parameter eta. Just by convention, I use dq just instead of writing d mu h of t, which would be more appropriate maybe. But I just like to say that we integrate over manifold of these matrices Q with invariant measure on T. But I will use this, maybe slightly abuse of notation, but I will use this dq in what follows. I hope it's understandable.
I didn't. So what did you do with the I integral? I didn't follow that.
With I integral, I just, you see, after this scaling, it's of order of 1. It does not have n, capital N, any longer in the limit. So I just replaced, as according to standard procedure, R's with saddle point values. And this precisely, now we see that precisely it goes, this becomes Q, or if you, yes, Q, this becomes S, so Q times S.
Okay.
That's it. And this integral should be evaluated, you should calculate it. Which in principle, I mean, it should be doable job, but you need explicit parameterization for T. I proceed in doing this. Okay. Now, precisely as Tom said, we need to evaluate this integral to know what is value, if we are interested at all. Maybe we are not interested much. But if we are interested at all, we need to calculate it. Basically, the matrices T can be explicitly parameterized using two real variables. One variable theta, which changes between 0 and infinity, and one circular variable, which goes over from 0 to 2 pi, just some angle. And this is explicit parameterization in terms of hyperbolic functions. In particular, this explains this hyperbolic function, explains the name hyperbolic symmetry, although even geometrically we shall see that this is hyperboloid. So one takes this T, it's very easy to calculate inverse of T, multiply with S, we end up with such a simple expression. So this is T. Now I said that this d mu h of T is invariant measure on this T, but how we in fact calculate. Here I just show a simple recipe how to calculate this measure. There are various methods and you can use whatever you wish, but it's just a simple calculational tool. Maybe I just demonstrated on the simplest possible example. Suppose you are just in two special dimensions, just usual Euclidean plane. Consider just length element dx squared and dy squared, and you like to calculate it now. You'd like to make basically change of variables and go say to polar coordinates when x equal to r cos theta and y equal to r sine theta. Of course, you know how to calculate the Jacobian. It will be that you'd like to know what will be the Lebesgue measure in these variables. We all know it will be r dr d theta. But the trick, if you don't like to calculate Jacobian, then there is a simple way of doing this, in fact, which is repeated here. You just you differentiate this, you differentiate that, you substitute it here, and you will see, okay, let us do it. Dx is dr cos theta plus minus r sine theta d theta. Dy equal to dr sine theta plus r cos theta d theta. Now, if we square this, square that, we see that cross terms go away and add them up. We see that dl in u variables, dl squared is just nothing else as dr squared. Dr squared, cos squared plus sine squared gives 1, plus r squared d theta squared, which I write using metric tensor. So it's basically, if you'd like, it's quadratic form. dr d theta, 1 r squared, 0, 0. Okay, dr d theta. So this is my metric tensor, G. And I should take, find determinant of G, take square root of it, and this will be my Jacobian factor, which enters Lebesgue measure in U coordinate. This is technical, but very, very useful trick. In many situations, quite complicated manifold, this allows you much faster to calculate things than just directly evaluating Jacobians. Please do it here. Natural invariant length element, so to say, on this manifold is just trace of dq squared, just for convenience, 1/2 you may put in front, it does not change anything. And you see then that your measure is just hyperbolic sine of 2 theta times d theta d phi. And this is basically this invariant measure on manifolds of T matrices that I made, or this which I should use for dq in evaluation of that integral. Now things are simple. I substitute it. Everybody can evaluate such simple integral. The result is, please.
I've got a question. I'm a little bit confused when you spoke about the sigma model.
Yes.
It seems that, well, the degree of the correlation function that you want to look at somehow determines the model, the sigma model.
Yes.
So usually you shouldn't, well, if you've got a sigma model, shouldn't you be able to evaluate all kinds of correlation functions?
From one sigma model, no. Of course not. Why? Some particular class of correlation functions you will evaluate, but in general, they will be of maybe similar symmetry type, but they will be of increasing dimension. Matrices Q will be of dimension determined by the number of points in correlation function you'd like to. In general, there are some lucky situations when basically even for all very high correlation functions can be extracted from just 2 points or related. But these are lucky instances, and that's why usually only in these cases they are explicitly evaluable. But in general, no. It depends, of course.
Sorry.
Yeah.
So eventually, I guess you want to take derivative with respect to the z variables.
Not in this, but at the next level, when I will really evaluate a generating function for resolvents, but not here.
Yeah, because I think in some cases you can also just have put all the sources in one determinant.
You mean by sources you call these spectral variables?
Yeah.
What means in one determinant?
So for example, you don't need all these determinants, but you can just have.
No, you see, I just consider general general object as I managed to do. If I could consider, I don't know. Yes, this is basically the object that we deal with in this theory. I do not specify it any longer. Then I should tell if I need to calculate some particular object, for example, in supersymmetric version, which we are hopefully in the end of the day, not today, will come to. Then you should tailor your original generation function to produce this object after some differentiation. But this is a secondary issue. You should just, okay, it could be interesting thing to discuss for particular object, but general theory will be the same. Just your particular object will be slightly different. Okay, so we discussed how to calculate. So we see that basically this integral is singular as we expected, in fact. It's singular when imaginary part goes to 0, but the scaled imaginary part. This is typical for correlation functions involving determinants with opposite signs of imaginary part. If it just you had all the same, it will be not singular. Although it's not obvious from the very beginning, I mean, without any consideration, because inverse determinant always has poles, but averaging smoothes them out if you do not quench real axis between between opposite signs. So this is typical behavior. Now just to add to this hyperbolicity, just observation that if you geometrically, really, these T's parameterize hyperboloid because points, if you consider points with coordinates in positive real axis and Z complex, such that these vectors obtained from standard vector 1, 0 by all these rotations T, you see that all these points just lie on half of hyperboloid. This is really, I think this is real, the origin of the name hyperbolic symmetry probably. Or presence of hyperbolic functions, just to add that it's really related to hyperbolic hyperboloid.
The importance is not with the name.
Yes, but
Wigner understood that there's a difference between the situation you discussed right now, where these signs appear, where some of the energies or the Z variables are in the upper half plane and some others are in the lower half plane. This mixed case. This is just qualitatively different, as you've shown, from the previous case where all of them are in the upper or all of them in the lower half.
right.
This mixed feature introduces the sign matrix, and then in this analysis, the most important consequence is that what originally was a single isolated saddle point now is a manifold. In the limit epsilon to 0, the function that you're integrating is constant along a submanifold of the entire space of integration. And
Yeah. I think it was more or less probably clear from, yeah. Yes, please.
Just quickly, so we're at the case, we're at 0, basically.
You mean that I took all real parts? Yes.
Yeah.
Or everything can be repeated for any point in spectrum, even out of spectrum, if you'd like. Not very interesting, but it just some square roots. We will see later on examples of this. But I wanted to have really the clear-cut case. It will be slightly more notations needed.
But the main features like this dependence on the
Precisely. Depends on eta is everywhere within spectrum of this random matrix, within support of the spectrum, the same. It will be slightly different, slightly different when you in tuned way approach edges of support of the spectrum. But I won't discuss it any longer. It's a different story. And also, I don't think that it's that relevant to localization properties. Maybe relevant, but not immediately. Okay, so now, so basically I analyze that integral, so showing that method, but basically this way of analyzing it, it's not appeared not that long, and there is a standard and also under many circumstances very useful trick which I think you ought to know, and I will use it later on in some other situation. So there is an alternative way of analyzing the same, arriving to the same nonlinear sigma model, and I think it's need to be discussed. Also, there is some personal reasons for that, because for many years I somehow avoided analyzing important paper by Schaeffer and Wegner, and Martin recommended me, and really I enjoyed it, and now I'd like to present this method. I think it's a really nice method. But practically, let me remind you that there were two different methods of analyzing n equal 1 case. We used some invariants of the integrand, and precisely the case that we already have generalized and analyzed in detail. But there was also another trick of analyzing large n limit, which used so-called, in physics it's called Hubbard-Stratonovich transformation. I learned yesterday from David's lecture that also Katz was involved and some other people. I know Hubbard paper is 57, so I just wonder when Katz did it. But in physics it's usually, Stratonovich is present, but Katz is replaced with Hubbard. But it's the same, essentially the same trick, basically, which appears all over. It's a very useful trick. That's also why I wanted to add it to our weaponry, so to say. It uses the fact that something which is quadratic in variables in the exponent can be replaced with something which is linear in these variables, and frequently it's very useful if you pay a price of one extra integration or even one extra matrix integration, like in this case. So basically, in this context, Hubbard-Stratonovich transformation is simple Gaussian matrix integrals over. First, we start with assuming naturally the case when we can verify this formula. It's very easy to verify this formula if Q is just Hermitian matrix, because then this integral on the right hand side, if you just write it in entries of Q, it just decomposes in product of one-dimensional, or practically for complex case, two-dimensional Gaussian integrals, and in the end to one-dimensional. So it's trivial to verify, and you do this integral and you obtain the left-hand side. And this is precisely the object which featured originally, before even rescaling R with n, in our integrand. So let us replace this with that, change the order of integrations, and see whether it gives us, in n equal 1 case, it gave us immediately access to saddle point methods, and it was alternative way of arriving to the same result. Here, however, because of hyperbolic symmetry, we shall see that situation is much more tricky.
You really need the fact that Q is Hermitian. I mean,
No, I start with Hermitian case. Also, plan is as follows. I start with Hermitian case, then verify that Hermitian won't go. It's just impossible to take Q Hermitian. Then, because it disregards intrinsic hyperbolic symmetry. Then I will try to find a Q following Scheffer and Wegener, and it will be done.
It's natural to start from the Hermitian case, because after all, the integrand is e to the minus 1/2 trace q to the square. And that factor controls the convergence of the integral. And you would like to the Gaussian to decrease in every direction, and the hermiticity of q tilde is exactly what ensures that.
Okay.
At that point, you wonder, how could you ever do it with something different than a Hermitian?
Yeah, it would be, if you know nothing, it's definitely the first thing you tried, if you ever heard about Hubbard-Stratonovich transformation. So you try it, you change these orders of integration, and you then unfortunately see that you cannot perform integral over phi's because it's divergent. In contrast to n equal 1 case, in the case when S is non-trivial, not proportional to identity matrix, it fails. Why so? Let us analyze in more detail n equal 2 case when S is 1 minus 1. Our Q tilde integration here, our Q tilde, okay, it should be of course dq tilde here. It's just Hermitian matrix. R, we know what is how R is made of. It's positive, non-negative, positive semi-definite matrix made of these phi's. So you just see what is this term in terms of phi's, because it's quadratic form in these phi's. So you should see whether it's positive definite in order to be able to perform Gaussian integral. And you find that, okay, first two terms, they are okay, because their real parts are positive due to epsilon, but there is this term which does not have this epsilon at all, and minus sign appears here precisely due to hyperbolic symmetry because of presence, if you trace it back, of minus 1 here. And you see that it's real, not bounded from below, nor from above, in fact. And it's trouble. You cannot perform this integral. The integral is divergent. And this is because you disregarded intrinsic hyperbolic symmetry in Q tilde, and you should take it into account. The way out is non-trivial and was proposed again by Franz Wegener and Scheffer and Wegener. So I try to just to discuss the method as I understand it. Again, on the simplest possible example, just explicitly, just to show that everything goes through. So, okay, I even I don't know. I forgot already that. I just considered special case, but not just 1 minus 1, but Q1s and Q minus 1s. It goes through as well. But you can do it for Q equal 1. It's already everything there. So they suggested to consider, instead of this Hermitian matrices Q, just Q Schaffer-Wegner, I call it, for time being, constructed in the following way. They're constructed exploiting these properties of these hyperbolic matrices T. This will be important to take this into account. And they made of the two pieces. First piece is block diagonal, and blocks they are with the second lower block has minus sign in front of it, just for convenience. You can put plus, it doesn't matter, because both are just Hermitian Q by Q matrices. T are our familiar matrices, which I here write just explicitly. You can verify. This is just a convenient explicit form for these matrices T, where this small case T is just a complex Q by Q matrix. And using obvious, okay, if it's not obvious, then immediately to verify identity, matrix identity, you immediately check that T's in this form indeed solve this relation that they expected to solve. So basically, you remember before I showed you one case, then T was for one case, so T is complex number, it was written down as its phase, exponential of I phi. And it was if you just use hyperbolic sign for its modulus and allowing argument of hyperbolic sign going from 0 to infinity to keep it positive, you immediately see that you can, why it's convenient, because square root of this will be just cosine, hyperbolic cosine. So that's why it's very useful. But we will use this one. We see that essentially here we have object T times Hermitian conjugate of T, positive definite object. In fact, T itself is positive definite, is easy to see. But okay, we have here, whatever is T, we have T times T dagger is positive definite. And it's interesting, just simple again, algebra shows you that T times T dagger in fact has precisely the same form as T itself, but just T should be replaced with tau related to T by this relation. It's simple algebra. Now, let us use these taus, they are convenient variables, and write down explicitly this Q. I just write it for your convenience explicitly in 4 blocks. I just denoted this. I think in your notes that some of you have, these red bits, they disappeared somehow. So, but it's just for convenience. I just denote this Q1, Q2, Q, and Q conjugated. Now we need to calculate volume element, or like measure on these Qs. And for this I need a Jacobian from entries of Q to these P's and taus as independent variables. Fortunately, due to particular structure, calculating this Jacobian is very simple. You just observe that corresponding Jacobian has block form. I do not, there is a complicated block here, but I do not care what is there. But diagonal blocks, they are very simple. They are proportional everywhere to unit matrices. And just somewhere they contain parameter lambda. What's important, I just forgot. Here there is a free parameter lambda. We will use it for any lambda. And then we will use, in the very end, we will use lambda to tune to the required saddle point manifold. So lambda here is arbitrary, and we shall see later on it needs to be positive in order to ensure. It's written here. Yes, real positive. It's real positive. So we now calculated this Jacobian. So measure is very okay. I leave it here. Mm-hmm.
Does this in some way reduce to the Hermitian case if you didn't have any changes of sign? I mean, this I lambda ST star T.
What means reduces? It's obviously not.
If S with the identity.
If you replace T with identity.
If S was the identity.
If S will be identity.
It looked like the Hermitian case.
I never thought about that. No, I don't think it's still. Why it's? Let me see. It's if. Okay, let me see just whether it's this is Hermitian. Okay, this is not Hermitian piece, right?
Yeah, but I can answer this question. You should think what you learned in complex analysis that
Maybe, Martin, I understand probably what you said. Maybe you give this comment a little bit later because it will be more relevant when we discuss the shift of contour. And I think you. Oh, okay.
well,
if you like to
maybe
proceed,
that's the
yeah.
question right now.
Yeah.
So we can, when we do complex line integrals, we can by Cauchy we can deform. So as long as the integrand is holomorphic, integrand here is holomorphic, and so you can ask this Schäfer-Wegener domain. This is some submanifold, some real submanifold in some complex ambient space. You can ask, can I deform this by in a sense of homotopy? So continuously, without
Without
ruining the
resources,
topology.
yeah.
Can I deform it continuously into the Hermitian matrix? And the answer is yes. So this domain is related by a homotopy to the Hermitian matrices.
But not in trivial
However,
sense.
it has the advantage of fixing the problem over there. It now will allow Jan to do the integration over the original variables in a good convergent way.
Okay, this I'd like to proceed to show. Okay, so we now explicitly have relatively in these tau p variables we have a relatively simple expression for the measure. But you see, as Martin said, it's and we discussed, it's not the domain of Hermitian matrices. It's in fact you can look at it as some very twisted domain, and it's far from being obvious. In no way usual Gaussian integral is just product of usual one-dimensional Gaussian integral. So one should verify whether it's indeed a good domain for Hubbard-Stratonich transformation. But fortunately, it is easy to see by reasons that Martin mentioned. One can, you see, okay, we now like to consider this precisely the same integral, but with Q Schäfer-Wegener replacing Hermitian Q's. We just inspect what do we have actually in the exponent. We see that just by simple analysis, just explicitly writing this trace of Qs Schäfer-Wegener squared, we see that integrals are convergent. And moreover, we can absorb these nasty factors, these square roots, which in fact look nasty. We can absorb them, in fact, by simply shifting integral over p into complex plane, just absorbing them in p. In the same way as you calculate usual Gaussian integral, but with linear path, like here, if I is in front, how you do it? You complete the square, but effectively it means that you shift your contour into complex plane. Here it's practically the same. And after this shift, Q is very simple. You perform, you simply, really, your integral decouples into simple Gaussian pieces, and you calculate it, and you are back to your to the result you hope to have. So basically, although Q Schäfer-Wegener is not literally Hermitian, by deep reason that Martin mentioned, that it
It's a deformation.
it's deformation, or it's higher dimensional deformation of contour, if you'd like, of original integral.
If you understand Cauchy in higher dimension, you can shorten the proof.
Yes. In fact, in one of, I will, in the very end of this course, I promised literature. There is, in one of Martin's review papers, there is a very nice explanation of this short. But for me, I always like to have some things explicit. This is, you really can verify explicitly, and it's not much more difficult. So,
In principle, you've just hidden the difficulty in the
No.
integration domain.
no, in integration, but this will help me, because then I can change the order of integration and integral will be convergent, as we shall see. Let us see it. This is precisely our goal. Now let us use this version of Hubbard-Stratonich transformation. And verify that everything is all right. Okay. So, in the same way as before, we substitute this formula that we just derived, but we substituted, yes, we replaced this with such an integral. We check that we can change the order of integration because now this internal integral is well defined. We remember what is R. Okay, here I was a little bit more general, maybe I should not be, but then one case, therefore this phi is n by n. This R is n by n matrix because phi is n component, small case n component vector, but the structure is completely transparent. This quadratic form here, basically, it's, you see this matrix, which appears here. It's now fully positive definite because this piece, this piece is basically lambda times. Okay, maybe I need to write it down because it was on one transparency before. It was here. Let me just explicitly write down this Q Schaffer-Wegener equal to P1 minus P2, these are Hermitian matrices, minus I lambda S T dagger lambda positive. And this piece with taus is precisely T dagger. You can see that it's positive definite. So with non-zero epsilon, this is well-defined positive definite form. When as a quadratic form, if you multiply it with phi's from left and right, if we use that lambda is positive. So lambda can be arbitrary positive value, and we can use it as we wish. It's just, in fact, parameter in our theory when we can use it to our advantage. Now, as we just agreed, integral is all right, it converges. Gaussian integral of a quadratic form in the exponential always produces just determinant to, this is integral over complex vector, so it produces not square root of determinant as yesterday, but just determinant minus n, where n is the dimension of this internal dimension of these phi's. And finally, we'd like to arrive to our nonlinear sigma model. We remember that it's only valid in appropriate limit n to infinity scale in epsilon. So let us see how it comes out. So we rescale integration variables p in this way. Also replace, because lambda is arbitrary positive, so it's convenient to replace it with square root of n. This amounts to q getting this factor n in front of it. So, square root of n in front of it. When it's squared, it gets n. We have term determinant to minus n, this term in the integral, and we should perform integration over Schaffer-Wegener manifold. Now, next and the last step before doing the saddle point, we should presence of epsilon here is a slight nuisance, but we know it should be an exponential in the end. So we use the following. We just write that determinant minus n of epsilon plus something, or plus what? Plus ISQ. Just convenient to factorize it. Determinant minus a of ISQ times determinant. So I just take this factor and the sign of determinant, use that determinant of product as product of determinants. So it will be 1 unity matrix minus I epsilon and inverse of Q times S. Inverse of S is S. Also to n. I'm happy with this because it does not have epsilon in it. And now I use that epsilon is actually, okay, we know that epsilon times n is eta when n tends to infinity. So I just here have eta divided by n raised to power n. Of course, I have then exponential of something in the limit which does not contain n. It's usual trick. I just, if it's not immediately clear, I just use that determinant is exponential of trace of logarithm of 1 then minus something expanded to next term. I have n in front, n times 1 over n goes away, and other terms in expansion will be just small in 1 over n. So we end up in the following. I do not care here about overall constant. It always can be accurately done and restored. If you see in my lecture notes, I always like this symbol. I am not sure that it's standard, but I use it when I don't like to be accurate with irrelevant numerical factors, which in principle with due diligence always can be restored, and they play secondary role for our consideration. So the structure is like that. We see that second term as we expected. It has eta in it, and it does not have a large parameter n in front because of our scaling chosen. Now it indeed looks like we can perform this integral by saddle point method. Variation of this just gives you a saddle point equation for matrix Q, Q plus inverse of Q equal to 0, as it's easy to see. So it immediately follows that Q squared must be equal to minus 1 of dimension 2Q. And the question is whether at all this, you see, we live basically on this manifold. It's the triumph manifold. Whether we can reach this saddle point at all can we have it on our manifold in order to perform this saddle point analysis? For this, it's just convenient. Okay, I leave it here, probably. For this, we just let us consider Q square. Take this Schaffer-Wegener Q and square it. I squared it for you. You may check that I did it correctly. And this is expression, and we just ask whether we can have our saddle point on Q squared equal minus 1 on this manifold. And the answer is yes. This will correspond to choice P1 equal to P2 equal to 0, and selecting that lambda, this constant, is equal to 1. Then indeed Q squared equal to minus 1. And if we just look back, what this means for what is the saddle point manifold for Q itself, we just see that it amounts to minus IS T Hermitian conjugate. Playing a little bit with properties of T, using this very property of T that TST gives S, I mean group property, which defined these T's. We then we see that basically that our integration manifold is precisely the same that we obtained in our previous analysis. It's just precisely the same set of matrices, T, S, inverse of T. If you remember, this is what we called nonlinear sigma model manifold. This which we obtained with less efforts in our first method, but nevertheless, I think that these efforts were not just wasted, but I think it's important to have this method in mind. And also, I find it in some situations shorter way of deriving things than in our first method. So I will use it in supersymmetric version also. But in the end of the day, we see that we arrive precisely to the same integral over the same set of matrices Q. There is subtlety here, which if you, of course, I think it's impossible to trace just, maybe ingenious person could trace it, but there is some subtlety. in my first method, really, I integrated over invariant manifold of this. This dq was just standing as a shorthand notation for invariant manifold or invariant measure on manifold on these t's. Here, I started from some expression of q's in terms of these, you remember, p's and tau's. And I perform saddle point evaluation. And I will get some then measure in terms of these tau's. But if you just substitute saddle point values, you will be surprised. You won't get correct expression for invariant measure. So the question, technical but subtle question comes, why it's the same model? How one gets precisely the same invariant measure? And the answer is as follows. I hope you remember, or at least I repeat it now, that there are two steps in doing saddle point integral. One step, you just find the saddle point or saddle points. Then you indeed substitute in the rest. But you also do integration, this quadratic form of fluctuations around your saddle point. This here, it gives you non-trivial result. It gives you something depending on T matrices. And this precisely cancels unwanted factors in parameterization of Q and produces, you may verify, it's nice exercise, produces invariant measure on these two T matrices. I think this point somehow not that much discussed in literature, but when you really do calculation, this rises. I wanted to discuss it. Okay, I have 10 minutes. In principle, I had planned to discuss yet another way of doing this. But I think it goes beyond immediate goals of this lecture. If I had plenty of time, I would do it. You can find this alternative way of doing Hubbard-Saturnovich transformation. Okay, just few words. I hope I satisfied you that this is conceptually simple and useful method which can be used in many situations. But in physical literature, although maybe, I don't know, in first approximation, several hundred papers are written on the subject, and people use different version of Hubbard-Saturnovich transformation, which until recently was not appropriately justified mathematically. There are historical reasons for that. I planned to discuss it, but I think it goes beyond our goals. It has some advantages. That second method has some advantages. You see, here in this deformed version of Hermitian manifold, it's not in Scheffer-Wegener domain is not invariant under natural natural symmetry of our integrand, and therefore this is one of reasons why it was not that much used in the literature, at least by physicists. There is a choice of domain which respects from the outset this symmetry. That's why physicists wanted to use it and used it 100 times. But then it's a rather non-trivial problem how to justify Hubbard-Saturnovich transformation. I'm just pleased to say that full resolution of the problem was achieved very recently by our chairman, and we now know all about this transformation. But I included some comments. You will find it on 2 pages, which I skip now in my lecture notes. But I probably stop for today at this point. Thank you. If you had any questions, please ask. And next time, next time I'll start with introducing anti-commuting variables. I don't know, probably you do it before me. Okay, so you do it before me. I will probably do it slightly different, but hopefully equivalent way. And we will start with playing with anti-commuting or fermionic variable. Thank you.
To qualify a little bit, you gave me too much credit. It's due to your own efforts that this question came up, and some of the important ideas were found by you. And then the actual details of this were worked out by a student of mine, Jakob Müller-Hill. Yeah, so that was a lot of formulas.
But I hope with some explanation and with motivation why we needed them, that we could not avoid doing this heavy algebra. So basically now we understand in full detail, just bottom line of all these 2 lectures, how to calculate these objects. And if we believe that these objects are useful for something, we know how to calculate them. By themselves, they are not that useful. I know some uses, but they are not extremely useful per se. But when combined with positive powers of determinants, so when considering ratios of determinants with various parameters z's, they're extremely useful. They can be used to generate moments of resolvents. And this is what we are after in random matrix theory, in localization theory, and all that. So this is our motivation.
Maybe one comment. David Bridges did a Satonovich transformation, and formally Jan did the same thing here. In David's case, he used it to decouple the easing, the interaction of the easing model, reducing it to a model sort of in an auxiliary field, where the easing there was then appeared linearly in the Hamiltonian. That allowed him to compute the sum of the partition sum of the easing spins explicitly, and write it as a new problem formulated in terms of something close to a Gaussian measure. So here, the same idea was used, but technically it's more difficult in the case with this mixed signature, because you're really struggling with this non-compact symmetry and keeping all the integrals convergent. So a lot of effort and thinking had to go into this. But the end result is very useful, because it somehow, like in your case, it introduces the good variables in which to proceed further. I mean, we are not so much interested in single random matrices, because there's many other methods around, orthogonal polynomials and so on. But the good thing about this method is it's robust. It just can be extended to more interesting models, models that reflect the spatial structure.
Hopefully this will be last 2 lectures in my course.
An orbital model of Wegener, again Wegener, can be treated with these methods, and so one has a way of approaching interesting models of real physical systems.
Okay.
All right, everybody's hungry, so let's go eat.